Right, thank you very much. So good to be back here, my first time in person since COVID. So I will try to tell you things about how the goal of this basically is to revisit geometric constructions in mirror symmetry, how you build a mirror using, I would say, the Strominger-Yau-Zaslow philosophy as amended over time, and how certain things that we've been taking for granted fail when there are holomorphic disks of negative index into the picture. And of course, that will only happen in certain cases, but when it happens, it's interesting. So the plan of the talk is really today, we are going to revisit SYZ mirror symmetry on a specific example and see what happens with it. And then tomorrow, I'll try to explain a possible framework for rebuilding what I'm kind of breaking today. So let me start by reviewing what I mean by SYZ mirror symmetry. So it's a process for constructing geometrically the mirror to some mirror to a given manifold X, symplectic, but in practice Kahler, relative to some anticanonical divisor in it, D. So you call that a log Calabi-Yau pair, if you want. Now, compared to some recent papers of Gross and Sieber, for example, I'm not going to try to build just a mirror of X minus D, but rather I'm trying to really build a mirror of X, including the divisor. So the starting point of SYZ is a Lagrangian torus fibration on typically the complement of these over some base B. And the general assumption I want to make is that the fibers of this phi are going to have vanishing Maslov class, which means they have a Z-graded Floer theory in the complement of D. And they are going to have generically, most of them, at least I would hope, don't really bound holomorphic disks, or at least there's some sanity into the picture. Okay, so step one is to try to build first what I would call an uncorrected mirror of X minus D. So a space that will be an analytic space. Locally, it will look like some algebraic piece of an algebraic torus. And the way it will be built is by considering pairs where I look at a fiber of phi, one of my Lagrangian tori, and a unitary rank one local system over it. Okay, so you could say these are objects of the Foucault category supported on the fibers of phi. I'm not going to tell you about what to do with singular fibers today because it's kind of orthogonal to my main point. If I say this, of course, there's a problem with singular fibers in this uncorrected mirror. This problem fixes itself at the next stage when accounting for wall crossing transformations.
When you say analytic space, you don't see?
No, over the Novikov field. And I will tell you what the analytic structure is. That's my next slide. Don't worry. I'm still trying to just first tell you what's the general plan, how we build a mirror, and we're going to elaborate on that, and then we're going to see an example where something breaks. Okay, so the next phase is to correct the geometry of the mirror to account for holomorphic disks in X with boundary on the fibers. And in fact, there's several kinds of corrections coming in there. Some already exist in X minus D by the assumption of vanishing Maslov class. Those are disks of Maslov index 0, and they are responsible for what's sometimes called wall crossing, and they will correct the geometry of the mirror. And then disks that intersect D will further correct it. Yes?
Unitary means like positive, recently, like.
I will define what I mean by unitary. Here I mean the polynomial along anything has valuation 0. Okay. I think I will define it, but if not, anyway, it will mean polynomial has valuation 0 in along every loop. Okay. So how holomorphic disks correct the geometry of the mirror is primarily governed by their Maslov index. So the Maslov index, if you're not symplectic geometer, this is like basically twice a relative first Chern class. It measures basically the degree of a determinant tangent bundle relative to a trivialization at the boundary along the Lagrangian, given by the tangent planes to the Lagrangian. And even simpler in our setting, because of this vanishing Maslov class assumption and because the divisor D represents the first Chern class, the Maslov index is just twice the intersection number with D. Okay. So when the Maslov number, when Maslov index is 0, we get disks that will contribute to deforming the analytic structure of a mirror. This is what comes up, for example, in Gross and Siebert's reconstruction problem, where they build wall-crossing scattering diagrams and the whole reconstruction algorithm. I mean, probably before Gross-Siebert, you should have also, say, Kontsevich-Soibelman. Okay. And the good news is these corrections also fix issues with the singular fibers. Because walls of Maslov index 0 disks come out of these singularities, somehow once you incorporate them, there's no, well, I mean, there are issues, but the issues are kind of well understood and not problematic. So the other thing that's well known, right? So the other thing that's well known is that Maslov 2 disks, the ones that intersect the divisor D just once, are going to contribute something we call the superpotential, which will be a regular function on the mirror. And that will make the mirror a Landau-Ginzburg model. So this is like the usual thing we see, starting already from toric Fano varieties and well beyond that, that the mirror might want to be a space that at first glance looks like the open Calabi-Yau that's mirrored to X minus D, further equipped with a function W on it that counts the contributions of adding back in the divisor D. And so the goal for today is to explain what happens if there are also negative Maslov index disks into this picture. So these are disks that have negative intersection number with D, and you may rightfully say, wait a moment, a holomorphic disk should intersect positively with a complex hypersurface. How can this happen? Well, the answer is this can happen if you have a disk that intersects D positively together with one or more spheres contained in D with sufficiently negative normal bundle. And then if you deform the complex structure generically, or if you just do the right thing for enumerated geometry, you'll find some counts of such disks. And when they happen, the claim is that this produces further deformations of a mirror geometry that make the mirror no longer be an analytic space, but rather something slightly deformed away from that. And so that's basically the slogan and the point of the talk today, is to work through this on an example and see what happens and figure out how to make sense of it. So let's restart from the uncorrected mirror. What's its analytic structure? And then we'll introduce the corrections. So first we start from a Lagrangian torus fibration on the complement of D. And I've said the uncorrected mirror should be the space of smooth fibers of pi. I'm just going to discard the singular fibers, which means I'm missing part of the mirror, but let's not worry about this. Together with local systems, I will just think of them as having some holonomy. So the holonomy of a local system is a homomorphism from the fundamental group to the rank 1 unitary group over our given field. I'll tell you in a moment what the field is and so on. We can talk about that again if you want. And so, whoops, that is not at all where I want it to be. Okay. And so that would be the first cohomology of a fiber with coefficients in U1. So I claim this has a natural structure of analytic space away from the singular fibers. And the simplest way to explain how a space is analytic is to just give a bunch of local coordinates that will define the analytic structure. in this case, it will be manifest how they change. So to pick local coordinates, I'm going to pick first a basis of the homology of a fiber, gamma I, and locally a base point, B0. And then I will define a local coordinate, Zi, at a point FB and blah, blah. This will be given by, so first of all, there's a coefficient, which is dictated by the symplectic area of a two-cycle that I call gamma I. Gamma I is the cylinder swept by the loop little gamma I as I move between my reference point B0 and the point B. This is called, for symplectic geometers, this is called the flux of a Lagrangian isotopy from B0 to B. And then I will multiply this by the value of the holonomy of the connection on gamma. What's my field? Time to say it. It's a Novikov field in one formal variable T. So it's power series whose coefficients are really in pretty much any field you want. I like to think of complex numbers because I'm not at ease with others. But I don't think it matters too much what this little k is. But the exponents of the power series are real numbers. And the requirement is that the exponents go to infinity. So there's only finitely many terms below any given value of lambda. Okay. So this has a valuation. Which goes to, basically this is the min of a lambda I. And we say an element of K is unitary if its valuation is zero. So if the leading term is a constant term with non-zero coefficient. All right. So, okay, so these quantities, you see that these Zi's, if you move B0 somewhere else, they will just get scaled by some constant factors. If you change your basis of homology, they will just change by some monomial change of coordinates. So this is really looking like, a piece of an algebraic torus, K star to the n, up to monomial coordinate changes. So the reason for the Novikov field and for these kinds of coefficients is that this matches exactly with how in Lagrangian Floer theory we count holomorphic disks with some coefficients. Okay? So Lagrangian Floer theory looks at holomorphic disks with boundaries on Lagrangians, and all of the calculations you want to do there are defined using weighted sums over moduli spaces of holomorphic disks. And the weight of a disk is precisely given by this kind of quantity. If I have a holomorphic disk with boundary on FB inside X, representing a certain relative homology class, well, I will count it with a weight that I call Z sub beta, which is T to the symplectic area times the holonomy of my local system along the boundary loop. So in particular, the valuation of Z beta is equal to the symplectic area. So automatically, pretty much, it follows from this that Lagrangian Floer theory wants to depend on F and nabla in a way that is analytic with respect to these coordinates on the mirror. Because basically, as long as your moduli spaces of disks remain the same, for example, if you keep the same fiber but change the local system, or you move it but there's no transitions happening in the moduli spaces of holomorphic disks, then you're counting the same things, but with these coefficients, Z beta varying from point to point. I should probably have pointed out, almost by construction, these Z betas are monomials in the coordinates up here, where the exponent has to do with the expansion of the boundary of beta in the given basis of H1, and the constant term has to do with the amount of area at the reference position. Okay, so now when I say it's automatic, well, there's a lot of details to be sorted out, but from there, we get to this family Floer approach to mirror symmetry that was explored first by Fukaya, then by Abu Zaid, and there's also work by Greenwood too, and by Heinz and others, probably. Okay. So now we need to talk about how we will correct this. Okay. So if there are no holomorphic disks in sight and maybe no singularities or anything, then this space of pairs consisting of smooth fibers of pi and local systems with its analytic structure is a good moduli space of objects of the Fukaya category of X minus D supported on the fibers. And with this analytic structure that we have, Floer theory seems to depend nicely on the point of the mirror. So holomorphic disks will, of course, deform everything in Floer theory. And the most basic way in which we do so is using this obstruction thing called M0, which is an element of the Floer complex of a Lagrangian with itself for every Lagrangian. So this comes out of Fukaya O Ota O. So M0 of a Lagrangian comes out of counting holomorphic disks in X with boundary on L with one marked point at the boundary. So you look at the moduli space of holomorphic disks representing a given class beta, holomorphic maps with one marked point in the domain, and so mod automorphisms of the domain. And this has an evaluation map at the marked point, telling you where the marked point went on the Lagrangian map. And schematically, M0 is a sum over all possible classes of disks, if we could say non-zero classes. You look at all the disks in this class beta. You look at their evaluation push forward. You look at basically what are all the possible points on all the boundaries of all the disks in a given class beta. That will be a chain on your Lagrangian, in my case, F beta. And of course, you weight it, you give it this Floer theoretic weight for this given class, and then you sum over all betas. And you interpret that somehow as a cochain in F. Now, what that means exactly is tricky. It depends on what kinds of cochains you use for the Floer complex. Tomorrow, I will tell you some more technical details about how to set up Floer theory. But meanwhile, if you have your favorite version of Floer theory, whether it's something that involves Kuranishi structures or something that involves Morse theory or something, you can set up M0 to be that kind of cochain on your Lagrangian with coefficients in the Novikov field. And observing there, the terms corresponding to a given class beta become something of cohomological degree 2 minus the Maslov index. For example, if you take evaluation chains, well, this moduli space has expected dimension given by the index theorem, n minus 2 plus the Maslov index. So it gives you an evaluation chain of codimension 2 minus Maslov index. So we expect now from, I would say, a lot of experiments playing with examples that in real life, in the SYZ setting, Maslov index 0 disks, for example, the ones that stay in the complement of D, will occur only along some union of codimension 1 walls in D. That's a lie. First, because there can be countably many such walls. In general, there's this so-called scattering diagram, which has infinitely many pieces. There's infinitely many different ways that you can have these disks happen. And the other problem is they're not even actually codimension 1 walls. In practice, they're usually thickened a little bit. It's only in the tropical limit that they converge to codimension 1. So it means in practice, to build a mirror, you need to proceed maybe inductively order by order if you go this way. But let's not worry about that. And then outside of these walls, we expect, usually, that the fibers are what's called weakly unobstructed. That means they don't bound any disks of Maslov index less than 2. So the only thing that happens is disks that kind of must happen. Maslov index 2 disks, if this dimension formula gives you n, the other things that will have to exist pretty much everywhere. But what that does for you is that the smallest dimensional family of holomorphic disks you can look at has the same dimension as the Lagrangian. And the problem you end up having is really, how do you count Maslov index 2 disks through a generic point of your Lagrangian? And that's what the superpotential will do. Okay, so for a class of Maslov index 2, the moduli space M1 bar has the same dimension as the Lagrangian. So the evaluation map has a degree, which is going to be some integer. And you count Maslov 2 disks in this way with the weights. And this is what we call the superpotential. This superpotential is, if you prefer, the coefficient of 1. By that I mean, the identity in cohomology, or the fundamental class in homology in M0. And the assumption is that outside of some walls, this is what happens. There's no other things happening. So technically, M0 being a multiple of identity means Floer cohomology is still well defined, at least for the Lagrangian with itself. The reason M0 is called an obstruction to Floer theory is because it is the curvature term in fact, a curved infinity structure on Lagrangian Floer complexes. And the only way that the Floer differential squares to 0 and defines the cohomology is if every M0 contributions cancel out. Okay. So I think this is kind of the review of stuff so far. Not really, there's more review coming up. Any questions at this point? No? Okay. So now we get to wall crossing and trying to understand what I said about how Maslov index 0 disks will tell me how to correct my error. Remember, so from the previous slide, we've already said basically Maslov 2 disks, what they will do is they will produce this function. And I haven't told you yet how we want to incorporate that into the geometry and how we define categories associated to the A and B models. But basically, the role of Maslov 2 disks will be to produce this superpotential. The role of Maslov 0 disks is what we'll see now. Okay. So the thing to note is this superpotential is analytic over the domains delimited by the walls because the counts of Maslov 2 disks remain locally constant. So these coefficients n beta, they're going to be locally constant. But then they will jump when disk bubbling happens as you cross a wall. Okay. So, picture of that, you might have a holomorphic disk in some class, we can call it beta plus alpha. And as I move in my Lagrangian fibration, at some point, there might be some class alpha of Maslov index 0 where a wall of disks in the class alpha exists. And my given disk of class beta plus alpha might break into a union of two such disks, and then this is a boundary of a moduli space of disks in the class beta plus alpha. But then, of course, the remaining component in the class beta persists and in fact exists also on the other side. There's also a disk in the class beta here. So if I compare what happens to my superpotential on both sides, on one side I have z beta plus z beta plus alpha, which I can factor. I mean, I didn't say it, but these like weights, they're multiplicative. Like when you add together two classes of disks, the weights multiply. So this is z beta times 1 plus z alpha, plus possibly other things. And on that side here, there's no more disk in the class beta plus alpha. We've lost the second term. And well, that's a change in our function. So now this is well understood in the community, but if you come at this from calculus or something, you have a discontinuous function, you're trained to think first of like, how much does the value of the function jump? And here that's the wrong question. Because instead, the statement is that there is a change of coordinates on the domain that cures the discontinuity. And this follows from the analysis of Fukaya, Ono, and probably other places as well. So the observation is that there is a wall crossing transformation, some coordinate change, which will basically take each z beta and multiply it by a power of some power series involving the weights of the Maslov zero disks that you encounter to some power, which is some geometric intersection number, algebraic intersection number between the class beta and the wall. And under this coordinate change, things will be fine. So if it's in this basic scenario here, all I do is I match z beta to z beta times 1 plus z alpha. The real formulas are more complicated because there could be multiple cover contributions or possibly attaching several copies of that Maslov zero disk. And so the statement is that we can build a corrected mirror by regluing the local pieces we had over each chamber delimited by the walls using these transformations, and then W will again be a regular function global. Now, if you are building the mirror to a Calabi-Yau, you're not even going to see Maslov 2 disks or superpotentials, but the wall crossing still happens. It's just that you need to probe it with something less primitive than holomorphic disks. Okay. Other quantities in Floer theory would also jump by wall crossing, even if there's no Maslov 2 disks. Just that Maslov 2 disks are the kind of easiest tool to really see those discontinuities. Oh. So the good news for most people is that these wall crossing transformations are usually going to be consistent. What I mean by that is if you cross walls in different ways to go from point A to point B in the base, you will get the same coordinate transformations. And so that tells you that yes, this process of regluing the pieces to build X-check is going to produce a valid analytic space. And in fact, this is the basis of something called the Kontsevich-Soibelman algorithm for computing the whole scattering diagram from the singularities of the base B. The Gross-Seibert program tells you how to produce from input data a singular affine manifold B with prescribed singularities. Then there's some standard analysis of what does the wall crossing transformation look like just for the small holomorphic disks near the singular fiber. And then you let consistency take over and you can figure out everything. At least conceptually. I mean, in practice, it can be really hard. And so the problem we have now is I claim consistency of the scattering diagram actually will fail if you have disks of Maslov negative index. So, convince you that this happens, main thing I will do today is walk through an example. So my example is going to be a fourfold obtained by blowing up some toric variety. I picked something where I suspect the Fukaya category will be trivial because I can do all the calculations there. You can compactify this example to something more interesting if you want to. It will just produce larger formulas that I don't want to show you. So what we'll do is we'll start from the product of C squared with the total space of a canonical bundle of P1. So if you want total space of O of -2. This is a toric fourfold. But I'm going to blow it up in a way that's not quite toric. And those of you who have seen me give talks here in the previous decade know that I love doing SOEZ mirror symmetry on blow-ups of toric varieties. Okay, so what I will do is I will blow up two different things. One is, okay, we should just open the picture. So torically, C squared, I'm going to draw moment map pictures because this is going to be close enough to the toric situation, but that's how you can make sense of it. And okay, so these are the moment polytopes for C squared and for O of -2. And then what I will do is I will blow up on one hand, I'll take the fiber of O of minus 2 over 0 times a line in C squared, and I will make it be parallel to the first factor, but I'll put it at 1 in the second factor, so that I can actually compare the geometry, if you want, at the second coordinate radius less than 1 and more than 1. I'm going to see some wall crossing happen as I vary the radius of my tori in the second factor. And similarly, I will also blow up 1 times C times the fiber at infinity. So that one should have been in red, in blue. So again, the fiber at infinity in O of minus 2 times a vertical line of center. Okay. And basically what will happen is this produces some kind of wall crossing between here and here, and we'll have some inconsistency happening here. So, okay, my divisor D will be the proper transform of all the toric strata. My Lagrangian fibration, there's a process to produce Lagrangian torus fibrations on blow-ups. That was a different talk a few years ago. I'm not going to get back into that. Let's just say that there is a way to lift Lagrangian torus fibrations, or more honestly to say, well, this thing still has a T2 action on KP1. We've destroyed the torus action on the first C squared by blowing up non-torically. But on the second factors, it's still there. And you can build a T2 invariant Lagrangian fibration by lifting Lagrangian tori on the reduced spaces, which all look like copies of C squared, but deflated in various ways around my 2 lines. So this produces something whose base still looks like R plus squared times the interior of delta. If you want to know, I can take here the moment map coordinates, where I do the toric reduction. And here I can take the radii of my tori in the C squared. Now, this will have some singular fibers where I hit the exceptional divisors in exactly the right way, because the blow-up produces a new fixed point of my T2 action. And so things near the exceptional divisors look different than they used to. But the good news is we're not going to need to look there. And so you can just forget everything else and just think that away from the exceptional divisors, the fibers are just going to be lifts of product tori in my toric variety. And the only thing that has changed, really, is that by adding these exceptional divisors, I'm giving holomorphic disks more opportunities to exist in there without intersecting D, or intersecting D differently. So in that sense, a blow-up, what it does is it modifies the Maslov indices of disks. Okay. So we're going to try to build a mirror to this, following the above recipes. And so let's start by talking about before we blow up. So there are well-known formulas for building mirrors of toric varieties. That goes back probably to Hori and Vafa first. And so what the formulas say is you're supposed to look at the fan, or if you want, like me, you're into polytopes, the normal vectors to the facets of the polytope. And you build a Laurent polynomial whose exponents exactly correspond to those rays of the fan. Geometrically, these correspond to Maslov index 2 disks, means they intersect D once, and they're just going to hit one of the toric divisors and be disjoint from the others. So they will look like a standard disk in some complex coordinate line and constant in all the other projections. So, for example, the mirror of C squared is just like two variables, Z1 and Z2, which are going to be the weights of these two disks, disk times point, point times disk, bounded by a product torus in C squared. So I'm embracing the fact that the coordinates on the mirror are exactly going to be the weights of certain classes of disks. Okay, so Z1 plus Z2, this is what you see already for a product torus in C squared. Z1 is the weight of this guy, which is disk times point. Z2 is the weight of point times disk. Now, what's happening here? So for a product torus in O of minus 2 over P1, the holomorphic disks that hit the coordinate planes. So there's one that goes straight down, in a fiber down to the zero section, and its weight is what I will call Z4. Here. And then there's two other divisors you can hit. And so there's some quantity Q here. I didn't say what it is. Q is T to the area of my P1 base divided by 2. Okay. So normalizing things suitably, you can arrange that these are QZ3 Z4 and QZ3 inverse Z4. And then we see the first hint of weirdness compared to the initial toric Fano prescription. This is not Fano because of that zero section having the wrong Chern number. There's going to be this extra term, Q squared times Z4. Q squared times Z4. That term corresponds to this disk union the zero section in O of minus 2, which is a rational curve with normal bundle O plus O plus O of minus 2 has C1 equals 0. And yes, you can attach it to that disk, and the count of those is actually going to be 1. You can check that if you deform the complex structure, this will persist as a holomorphic disk. The node will smooth itself. Okay. So anyway, so we have this thing. And now the game will be to redo the calculation with exceptional divisors in the picture and see what happens. So, okay. So the first thing to note is in the blow-up, the main transitions we have to worry is about the radius of my torus in the c-squared directions. Okay, and why is that? Well, if my radius is less than 1 in both factors, then the maximum principle implies really that my holomorphic disks, when I project them first under the blow-up map, then to c-squared, they will stay inside the unit ball, and therefore they will not see anything about my exceptional divisors, which I placed at 1 on the 2 axes. So if the torus is thin enough in the c-squared directions, it doesn't know anything about the blow-ups. We still have the same disks as before. As I increase the radius, there will be new Maslov 2 disks in the blow-up. And those will be disks that before the blow-up had higher Maslov index. So they intersected maybe simultaneously, say, this divisor and that divisor. They had total intersection number 2 with the toric divisors, but now I can rig things, arrange it so that one of those intersections happens exactly where I did a blow-up. And in that case, under the blow-up, it's going to miss the proper transform of the exceptional divisor. And so those proper transforms of higher Maslov disks will contribute to the superpotential index. Okay, so for example, let's start when the radius in the second direction has increased past 1, and the radius in the third direction is still less than 1. So I haven't noticed the blow-up that I've drawn in red here, but I've noticed the blue one here. Okay. Then, so you can basically work out, and it's like elementary complex analysis. I'm not sure I want to show you too much of the calculation. But the main thing that happens is there's 2 new terms, which are here and here. So what are these things? I mean, this one is easiest to explain. This is exactly, I take a disk that moves along this axis in the second factor, while also moving along the second axis in the first factor. So its weight will be really Z2, Q, Z3, Z4. And now these things have Maslov index 4 downstairs, so they exist in higher dimensional families, using the fact that, but now there's something I can do, which is arrange to reparameterize the 2 factors relative to each other, so that when the second factor hits this L0 that I'm blowing up, the first factor is exactly at Z2 equals 1. And then, under blow-up, this will still be a Maslov 2 disk. And it contributes this extra term. What about this guy? Same idea, but now what I want to do is I go down here, and I will attach this sphere, but I will arrange to do this whole thing here, exactly when this thing is at 1. So it's a disk that kind of, again, goes sideways, And then that one doesn't go near the exceptional divisor, but then I can attach to it this sphere that I call S hat at x2 equals 1. This is going to be the proper transform of one of these spheres that happens to hit one of my blow-up loci. So in fact, this one will have normal bundle O plus O of minus 1 plus O of minus 2. So it has, in the blow-up, it has C1 equals minus 1, and that offsets the Maslov index 4 disk. So I built a Maslov index 2 disk from a Maslov index 4 disk together with an actually negative sphere. And now you see if you have negative C1 spheres, this is a recipe for disaster pretty soon. Okay. So you can redo calculations similarly for when R1 is bigger than 1, and again for when both are bigger than 1. And it's kind of the same story. The slightly new thing that happens is this term here in orange. So this term in orange that only exists, oh, that should be plus plus, sorry. That term that only exists in orange is actually the proper transform of something that had Maslov index 6, if I'm counting correctly. Sorry. So that was a disk which in C squared was going to kind of go diagonally. In F2, sorry, in KP1 was going to go straight down. And I'm going to arrange that when it hits down here, I'm in fact at the point 1, 1, where both blow-up loci pass through. And then this sphere, when Z1, Z2 are, sorry, X1, X2 are 1 and 1, it's even more negative than the others. This is a particular sphere in there with normal bundle O of minus 1 plus O of minus 1 plus O of minus 2. So it's very exceptional. And that gives me something, again, that contributes to the superpotential. Okay. I'm boring you with these calculations. You can just also trust, it's complex analysis in actually one variable at a time. There's really nothing elaborate here. So now let's talk about how the wall crossing works. So we know that when the radius crosses 1 in either direction, there's going to be some changes. Our formulas have jumped. How can we capture that? So the next thing we can do is understand what kinds of disks exist of Maslov index 0 or less. And a consequence of that is that the wall crossing at R1 equals 1 only affects the Z1 variable. The only disks affected by that wall are the ones that go along the first factor, because they're the ones whose intersection number with the wall will be non-zero. And so all we have to do is find actually a formula for correcting Z1. And we can. This formula changes this Z1 to this whole term here and makes the two formulas for the superpotential match. And you can interpret these terms as indeed being contributions of Maslov index 0 disks or stable disks that happen on the wall. You can do the same thing in the other regime where R2 is bigger than 1. There's a similar coordinate change, which now includes 3 kinds of Maslov 0 configurations instead of 2, because there's the extra one that passes through 1. Through R2 equals 1, you can do the same thing. It's only Z2 that will change. And again, there's 2 or 3, depending on the value of the other radius, configurations of Maslov 2 disks. And again, some of those Maslov 0, and some of these Maslov 0 disks are genuine disks. Most of them are actually positive Maslov disks together with negative spheres. Of course, you need to check the regularity of those configurations, but that's not very hard. And now, okay, you think you're done, and you are done. You've built a mirror. There are 4 coordinate charts modeled on domains in K star to the 4 with functions on them, and there's coordinate changes. There's only one small problem, which is that the coordinate transformations don't satisfy the co-cycle condition. Okay, so you can ask, well, okay, maybe there's a calculation mistake. I mean, you're welcome to check. I don't think there's a calculation mistake because I have an explanation for the inconsistency that's consistent with the outcome. So hopefully it's okay. The explanation is that when I'm down here at both radii being equal to 1, there's a Maslov index -2 stable disk. That disk is just, I go straight down here, and then I add this sphere. And because I'm at 1, 1, I'm actually on both blow-up loci. And that means here, I'm actually not going to intersect the toric divisors. I'm going to pass through the exceptional divisors. So it's a disk of Maslov index 2, going down, together with a sphere of C1 equals -2, or Maslov index -4. Okay, and that thing has this weight Q prime Z4. Okay, so how does this Maslov -2 disk pose problems with consistency? Right, I didn't explain it. Okay, so the reason that, what consistency usually is about is the statement that the boundaries of the moduli spaces of Maslov index 0 disks will be fiber products of pairs of Maslov index 0 disks over evaluation maps, expressing the fact that, I've told you before, Maslov index 0 disks, we mess up Maslov 2 disks by, they bubble off and that's the end. But they also mess themselves up because they can break into pairs of Maslov 0 disks. And the fact that, when this is the only possible way that Maslov index 0 disks can break off, this is exactly what causes the consistency condition where transitions happen. This is kind of the heart of the Kontsevich-Soibelman consistency condition. It comes from this feature that, this thing, you can recast this into some kind of Marov-Karpen type equation, which I will do next time, actually. And the problem we have now is that Maslov 0 disks can also break into Maslov 2 and Maslov -2. And that is not part of the story about consistency of real process. Okay, so let's talk more about what happened exactly. So maybe we should go back to here. So the inconsistencies, they come with this weight Q prime, Q double prime. So these are, Novikov weights of proper transforms of those spheres, times Z4 is the weight of this disk, times, and then like here I have Z1, Z2, Z2, Z1, and so on. Anyway, what's going on? So the first observation, which would be easier if you had still the whole picture there, is that the only inconsistent terms are those terms that involve Q prime, Q double prime. So mod Q prime, Q double prime, if you imagine that somehow, contributions of things that have proper transforms of the spheres would go away, you wouldn't see a problem. And so mod Q prime, Q double prime, this mirror is consistent. And then you can think of the extra terms as a deformation of the mirror with those terms discarded, which was completely consistent. So what is this deformation? Where does it live in? Well, each of these classes of disks that show up, you should think of them on the Fukaya side, contributions of holomorphic disks are Hochschild cohomology classes, or maybe I should say before you make it consistent, just Hochschild co-chains on the Fukaya category. And so on the mirror side, I should get something in the Hochschild cohomology of the category of matrix factorizations of my previously corrected but not completely Landau-Ginzburg mirror. And there's a calculation of, I believe it's Lin and Tomer-Leano, which tells us that this Hochschild cohomology is in fact a cohomology of polyvector fields on the mirror, but with an extra deformation of the differential that adds interior product with the superpotential. So now a deformation coming from a Maslov -2 disk should have total Hochschild degree 4, because this thing, again, like everything else in this story, lives in Hochschild degree, in cohomological degree 2 minus Maslov index. And the leading term of this deformation, which I will call W2, is going to be, in fact, a 2 co-cycle, sorry, 2 co-chain, 2 co-something, with values in the second exterior power of the tangent bundle. Namely, I will arrange that, on the overlap around 1, 1. So you could say, wait, this is a quadruple overlap. What's going on? Yeah, but discard 1. This morally works like a triple overlap. Okay, it's a codimension 2 overlap in my base. On this overlap through the center, it will take values. So this is the weight of my Maslov 2 disk. And this is the direction of the, I don't know what to call it. It's not a wall anymore because it's codimension 2, a strut maybe or something, of Maslov minus 2 disks. They live in the direction of dual to Z1, Z2. They are exactly where the radii R1 and R2 are fixed, and they vary freely in the other two vectors. So I can try to build, I would like to build a cohomology class in here, whose main term, like the most interesting term, is a check 2 cochain with coefficients in wedge 2 of the tangent, and is this on the overlap. And now, sorry, yes?
Do you have some explanation for P minus Q is still 0?
Sorry, what is P minus Q?
Say the power, and take the power of the exterior power and the.
Yes. So I will say this is tropical geometry at work. Okay, so what I mean by that is all of the collections of holomorphic disks I will see in SYZ, I expect them to have some tropical depiction on the base, where what they do is they kind of fill some kind of, locally they kind of want to live along some algebraic cycle or something. The walls, they self-propagate along the very holomorphic curves that they are made of. And so my vague impression is tropically, it's kind of, this thing wants to have codimension 2 in the base and codimension 2 in the fiber, because this is what the tropicalization of a complex codimension 2 algebraic cycle or analytic cycle, whatever complex, codimension 2 complex submanifold wants to look like. Again, that's a little bit of, faith at the moment. The tropical argument is pleasant, but I can't really justify it. In this example, it's kind of clear. I'm just saying in this example, it's codimension 2 in the base, codimension 2 in the fiber. I believe that, tropical intuition should tell you that this wants to happen when you're sufficiently close to the large complex structure limit. But I don't know for sure. So the thing to note is this thing in itself is not closed because, in particular, if you do its interior product with dw, it's not closed under that and so on. So to build it into a cocycle in here, you actually need to add terms which live in C1 with values in the tangent, and even in C0 with values in the functions. So the terms of order 1, I can just take, these things are exactly the terms I put in my coordinate transformations. Here, see this term, Z1 goes to Z1 times that. I can say I'm flowing the vector field Q prime, Q double prime, Z2, Z4, DD log Z1. And same thing for the other side. And then the change is also in the superpotential. So basically the terms with Q prime, Q double prime, I will interpret as all being part of this deformation of my Landau-Ginzburg model. So these are like the, unexpected terms of something in the wall crossing transformations. And this is the term in the superpotential in the upper right corner that also goes with that. And you can check now that these things together are indeed closed under D plus interior product with dw. Namely, the interior product of D of the main superpotential W into W2, this guy, is going to produce exactly the check co-boundary of W. And the interior product of dw into W1 will produce the check co-boundary of W0. Okay. And so where we are at is now that X check is going to be a deformed Landau-Ginzburg model in some sense. It has, okay, it starts with an X check and a W, but we've added some little bit of a mess to that. And the way you should think of this mess is now you have a space that's built from analytic charts with W is an analytic function in there. They are glued together by coordinate transformations, which are analytic and under which W matches, but the coordinate transformations don't quite satisfy the cocycle condition. The cocycle condition is deformed by this additional term. So tomorrow, it's a preview of tomorrow, will be how do we actually encode what's happening? And I'm just going to show you everything, and then I will kind of leave you in peace with that. Tomorrow we'll restart from here. The claim is, I believe, that there should be a way to understand all of the corrections at once, rather than start from the consistent ones and then add the mess that we got from that negative Maslov disk as an extra deformation. The proposal is that we are going to look at the uncorrected mirror first, and we are going to do Lagrangian Floer theory, not just for one fiber at a time, but for all of them simultaneously. And we are going to encode that in a family M0, which will be a co-chain on the, well, really on X, you could say, but I'm thinking of it as on the base with coefficients in the fiber, with coefficients on a certain sheaf where exactly those Z betas live. And this thing, so the expectation is that it will again be a sum of terms that live in codimension 1 in the base and have codimension I in the base, codimension I in the fiber, corresponding to codimension I families of Maslov 2 minus 2I disks. And the next expectation is that this M0 satisfies a Maurer-Cartan or master equation. And I'll explain to you why this produces a consistent, extended deformed Landau-Ginzburg mirror almost automatically if this equation holds. So the plan for tomorrow is to kind of tell you more carefully what this is about, how we're going to set up this M0, how we might try to prove that it might satisfy the master equation. I don't have a complete proof, I have parts of something. And yeah, and basically what this is about. Okay, thank you.